Okay, so coming back from our break, remembering where we were when we left.
No idea.
Well, we had been talking about this unit circle thing. Pretend that's a circle. Okay, we can't pretend that that's halfway through. It's not even close. Pretend that's the middle of the circle. There and there. Wow, I'm horrible today. Yes, you do. So if that's my angle right there, I'm going to call that theta.
I know what we're talking about.
What's this dimension right here mean?
Sine.
Sine of theta. Very good. What's this dimension right here?
No.
That is the cosine. That's the adjacent side. Now if I extend this here out like that, I've got to draw another line to intersect it like this. Of course, this is at a right angle to the radius. This purple one here is called the what? That is the secant. And the green one is called tangent to theta. Very good. Now the cosecant and the cotangent would be up here. So this would be the cotangent theta, and then out to here, that would be the cosecant of theta.
If it leaves the circle.
Yeah. Secant and cosecant always go through the circle. They always go past the radius. Remember, this radius from here to here is how much? 1 unit. Always exactly 1 unit. So sine and cosine are always inside the circle. So they're always less than or equal to the radius. So they're between -1 and +1. Secant and cosecant always go through the circle, outside of the circle. So they're always larger than the radius. So those are always larger than 1 or smaller than -1. They have an absolute value of bigger than 1, always. Tangent and cotangent are outside the circle, but they can be, tangent at 0 degrees is nothing. As you get close to 90 degrees, tangent shoots up to infinity. So tangent and cotangent are the two that can be any value. But sine and cosine must be between -1 and +1. And secant and cosecant can be anything but between -1 and +1. So when I actually look at a right triangle, if this is the angle I'm looking at, I'm just going to call it angle A for now. Of course, this will be angle B and angle C. What's this side going to be labeled? Little a, little b, little c here. They're always labeled by their opposite angle. But now, because this is a right triangle, we do have the right angle here. This side has a name. It's side C, but it also has a name, which is the hypotenuse. The hypotenuse is the one side of a right triangle that does not depend on which angle we're looking at. The opposite and adjacent depend on which angle. If I'm looking at angle A, this is which side? The adjacent, because it's next to angle A. This would be the opposite. If I'm looking at angle B, this is now adjacent, and this is opposite. So the opposite and adjacent depend on what angle we're looking at. So the sine of angle A, let me give myself a little more room here. Come on. Sine of angle A, remember sine is opposite over hypotenuse, right? So that would be A over C. Cosine of angle A would be adjacent over hypotenuse, or B over C. Tangent of angle A, opposite over adjacent, so A over B. Cotangent of A is adjacent over opposite. The B over A. Secant of A. Hypotenuse over adjacent. So C over B. And cosecant of A. Hypotenuse over opposite. So C over A. Sine B is opposite over hypotenuse, but from B, the opposite side is B. So B over C. Cosine of B. Adjacent over hypotenuse, but from angle B, adjacent would be A over C. Tangent of B. B over A. Cotangent of B. A over B. Secant of B. Yep, and cosecant of B. C over B. Now, some things to notice here. Sine A and cosine of B are the same thing. Why? What's the relationship between A and B? Their letters? Well, this is 90 degrees, right? And in a triangle, all the angles must add up to 180. So these two must add up to 90. 180 minus 90 leaves us with 90 for the other two. A and B are complements. Because they're complements, remember the definition of cosine is the sine of the complement. So the cosine of B has to equal the sine of A because they're complements. Likewise, the cosine of A has to equal the sine of B because they're complements. How about tangent of A? That should equal cotangent of B because, again, they are complements. Cotangent of A is going to equal tangent of B. Yeah. Cosecant means the secant of the complement. So cosecant of A is asking what's the secant of its complement. Well, the complement is B, so it's equal to the secant of B. Or same here. Cosecant of B is asking what is the secant of its complement. Well, its complement's A, so it's equal to the secant of A. So if I give you that the sine of A equals 0.734, and if I tell you that A plus B equals 90 degrees, let's go cosine of B. 0.734. Cosine of A is equal to sine of B. Cosine of B is equal to sine of A. You're trying to subtract from 1. Now, in your calculators, let's see if you can remember how to do this. Find for me the sine of 30 degrees. .5? Give everybody a chance to make it come out. Yeah, test it, make sure your calculator comes up with it, though. Yours works. How about the cosine of 30 degrees? 0.866. Oh, you're in math type mode. Yeah, that's the same thing. Tangent to 30 degrees? 0.577, you got it. How about the cotangent of 30 degrees? Remember I do this one? You're going to do tangent 30 degrees, close your parentheses, and hit that reciprocal key, x negative 1 or 1 over x, 1 over box in some years. So it's going to be 1.732. So on your calculator, you're going to do tangent 30, close your parentheses, and then hit your reciprocal key like that. Did it work? So on yours, Richard, you do tangent 30, close parentheses, then you got that 1 over x, or 1 over box key.
No, I had the double pump key that you have to hit twice.
Oh, bring it up here. No, you're talking about inverse tangent, not, you're a step ahead of us. So on yours, you do tangent 30, close parentheses, you get the 1 over box key, so you shift that. You're thinking inverse tangent. So, everybody get that to come out now to 1.732? How about secant of 30 degrees? Secant goes off of what function? Cosine. Very good. Yeah, it's easy to remember tangent and cotangent, but secant goes with cosine. So you're going to do cosine of 30, and close your parentheses, and then hit that reciprocal key. Should be 1.15. How about cosecant of 30 degrees? Did everybody get the secant to come out? Cosecant, of course, then will go off of the sine. Should come out to be exactly 2. Yeah? Okay. So now, how do we reverse that process? If I tell you that the sine of A equals 0.8, A has to be what? Here's where we use the inverse sine. So it's going to be second sine 0.8. So we do this 53.13 degrees. Yeah, remember we talked about how, like, if it was 3x equals 15, you divide by 3, you do the inverse. Okay, so here now we have to do the inverse. So it's the sine negative 1 cancels out the sine. So it's sine negative 1 of 0.8 over here. So it's second sine 0.8. So this is where you have to use the double pump key, Richard. You get 53.13 degrees. So what if I tell you that this cosine of B equals 0.3? What's B got to be? 72.5? 72.54, yep. Everybody get 72.54 degrees? Usually angles I go to 2 decimal places. Trig functions I go to 4. Unless you're told otherwise. If I'm dealing with, like, going from degrees, minutes, seconds into decimal degrees, then I go 4 decimal places on the angles. That's the only time I usually go more than 2 decimal places on the angle. So if I tell you the tangent of angle C equals 1.9, angle C is going to be 62.24. Very good. Everybody get those last 3 to work? What if I tell you secant of D equals 3.5? Well, secant, of course, goes with...
So we got cosine negative 1.
So you do the inverse cosine, yep.
You got hit by the number 1 still.
This time, remember, you hit the reciprocal key inside the parentheses. When you're doing the inverse cosine, the reciprocal goes before you close the parentheses. So it's second cosine for inverse cosine. 3.5, I hit the reciprocal and then close the parentheses. 73.40 degrees. You ever get that to work? So the cotangent of f equals 0.4. How's that going into the calculator? Okay. The reciprocal is inside the parentheses again. Good. So second tangent, 0.4, reciprocal, close parentheses. 68.20. I'll tell you the cosecant of G is 4.1. What's G got to be? $14.12 under. $14.11698. Just read it wrong. Okay. It happens.
Well, if you said the cosine, you want to
Cosecant. So that's why it goes with the sine. Remember, that symbol means cosecant. Now your calculators now are capable of doing this. What's the sine of 420 degrees? .866. How did I know that? Well, it's because I know the sine of a related angle. Exactly. Here's our unit circle. If I start here and go all the way around, that's 360 degrees. Well, to get to 420, I've got to go, start going around again. This is 420 minus 360, or 60 degrees. It's what we call coterminal angles. When you're asked for the simplest coterminal angle, it's asking for an angle between 0 and 360. So 420 degrees, its coterminal angle would be 60. So sine of 420 is really the same as the sine of 60 degrees. Now, this is important in a lot of applications. If you get into radial motion or cyclical motion, or you're talking about the position of a shaft on a motor that's spinning or something like that, or if you're graphing the position of a spot on a piece of material that you're turning on the lathe, its height would go through a cycle like this. It'd spin once, that's 360 degrees, and it starts over where it began, and it goes around the same cycle again. Well, rather than just going up to 360 and stopping, you can graph that position over time. Here's 360, 720, 1080, and you know that at 0, it'll be at the same position as at 360 and 720 and whatever, because it's cyclical. It starts over. 360 is 0 degrees. 720 is still 0 degrees because they're coterminal. They stop at the 0 degree point. Once upon a time, before we had these fancy calculators that you can put in pretty much any, you can put in the sine of negative 20 degrees if you wanted to, and it'll do it. The first calculators only did 0 to 90 degrees. And we had tables that only went from 0 to 90 degrees. So we had to use that unit circle to figure out what the sine, cosine, and everything was. For example, let's look at that 60 degrees here. This is its sine right here. And if you punch it in the calculator, it's 0.866. Is there another spot where the sine is 0.866? That's also 0.866, isn't it? Well, this angle here is also 60 degrees. But that's not really the position of this terminal side. It's really at what angle is that at? 120. This angle here, remember we talked about this being what we call the reference diameter? This angle is what we call a reference angle, because it's the angle between the terminal side and the reference diameter. It's the smallest angle. And obviously 120 is a reference angle too, but we want the smallest angle, which is the 60 degrees. Because angles that have reference angles of 60 degrees have the same sine, or have related sines. Is there any place else that has a reference angle of 60 degrees? Well, sure, there's one here. What's that going to be at? Well, this is 180, right? Plus 60 is going to be 240 degrees. But it has a reference angle of 60 degrees. Its sine is related. This is going to be how much? It's 0.866, but it's negative. It's negative 0.866. This is below the axis. Same thing over here. This is going to be a negative 0.866. Its reference angle here is 60 degrees. That's going to be 360 minus 60, or 300 degrees. So 60 degrees, 120 degrees, 240, and 300 degrees all have reference angles of 60 degrees. So they all have sines of either positive 0.866 or negative 0.866. So once upon a time, when we only had sine or trig functions between 0 and 90, if I wanted to find the sine of 120, I found the sine of 60, the sine of its reference angle. If I wanted to find the sine of 240, I found the sine of 60 and made it negative because I know it had to be negative. How about cosine? Of course, cosine is this dimension right here, which is actually 0.5. Cosine of 60 is 0.5. Cosine of 120 isn't 0.5, it's negative 0.5. So in this case now, all the angles that have a reference angle of 60 degrees have a cosine of either 0.5 or negative 0.5. But you'll notice when it was sine, the 60 and the 120 have the same sign. But when it's cosine, it's positive 0.5 and negative 0.5. They're opposites. One's positive, one's negative. Where's the angle that has the same cosine as 60? Well, it's right here, the 300. Those both have a positive 0.5 as a cosine. So this unit circle, this picture, like I said before, your trig functions come off of a circle, not off of triangles. But if you can keep this unit circle in mind, it helps you a lot with these angles. One of the things we're going to come out with, remember we talked about doing the inverse sines and inverse cosines. If I tell you that the sine of angle A is 0.7, you punch in, okay, second sine 0.7, gives you 44.43 degrees. Is that the only possible answer for that? On my unit circle, there's 0.7. That's my 44.43 degrees. But there's also a spot over here that's 0.7. And that angle is at 180 minus 44.43 degrees, or 135.57 degrees. Make sense? Calculator is only going to give you this one. Only going to give you the acute angle. But there's an obtuse angle, the supplement, that's going to be the same. Now we're doing inverse cosine, you don't have to worry about that because it'd be positive and negative, so there is a difference. That one's going to be big when we get into it later. Any questions? Well, acute, obtuse, and right are the three angles for triangles. Scalene, isosceles, and equilateral. That's just over 360. So you use, it's called coterminal angles. By subtracting 360, you get something below 360. That's called the simplest coterminal angle. Because technically, 12 degrees, 372 degrees, 732 degrees, those are all the same angles. They're all coterminal. The simplest coterminal is the one that's between 0 and 360. Technically, negative 348 degrees is also coterminal with that. There you'd have to add 360 to get up to 12. And don't forget, we now know radians. That look familiar? Pi over 6 radians. Remember we said on a unit circle. No. Pi over 6 radians. What that is the angle, whatever angle I could put here. Remember, the unit circle has a radius of 1. Pi over 6 radians is saying whatever this angle is that gives me an arc length here of pi over 6. Now a full circle is how many degrees? 360 degrees. If this has a radius of 1, has a diameter of 2, which means it has a circumference of 2 pi radians, right? So that means it's 360 degrees equals 2 pi radians. Coming back to it all now? A little bit, maybe? In your nightmares? So let's say that I want pi over 6 radians. I'm going to convert it by doing 2 pi radians over 360 degrees. Radians cross cancel, pi cross cancels. 360 and 2 can be divided out to be 180 and 1. 6 and 360 divided by 6 to give me 1 and 30. Hey, all I'm left with is 30 degrees. The other way you could do that is this. Pi over 6 radians is to blank degrees as 2 pi radians is to 360 degrees. Now the key to doing this is I always cross out the pi and the radians right away. So it's just 1/6 times 360 divided by 2. Gives you 30. We'll cover that more later. It looks like we're going to need some more practice for that yet. Check and see if page 345 through 347 is in the packet I gave you before break. Yeah, pretty much. I think I have to give you a new packet for that one.
Sorry, 345.
Do I have to give you a new one?
We got 345 and 347.
Perfect. So that's in your packet. So 345 to 347 is in your packet. Do the odds on those pages. Should bring you up to speed. Hopefully tomorrow I'll walk in and the classroom will be ready to get started. So I don't have to sit here and whine for 10 minutes before we go. I absolutely hate it when somebody